Okay, so the first thing we're going to study is something called heat of reaction. So Q reaction, that would be heat of reaction. The heat of reaction is defined as the amount of heat absorbed or released during a reaction. So if heat is absorbed, that's endothermic. We say the reaction is endothermic. And heat is released, we call that exothermic. So whenever we run an exothermic reaction, we feel heat being given off. Whenever we run an endothermic reaction, that reaction feels cold to the touch because the system is absorbing heat from the surroundings, which would include your hands. So that's the difference between an endothermic and an exothermic reaction. Now, in thermodynamics, there is a quantity called enthalpy. Enthalpy is simply a measure of the heat content of a substance. So enthalpy cannot be measured directly, and we really don't care what the enthalpy of a given object is. All we care about is the change in enthalpy that occurs when reactants turn into products. So the symbol for enthalpy is a capital H. And what we find, if we look at our physics, and we'll see this when you get to physics, at constant pressure, the Q of the reaction is equal to the delta H for the reaction. So even though we talk about heat of reaction, and you'll see it sometimes written as Q reaction, you also see it written as delta H for the reaction. They are the same thing at constant pressure. And since most of the time when we're working in a lab, we're working at 1 atmosphere pressure, the pressure is constant. So Q reaction and delta H for chemists are pretty much interchangeable. Now a couple things about enthalpy and enthalpy change. Enthalpy is a state function. So what that means is that the amount of enthalpy change for a reaction is independent of how that change takes place. Whether it takes place in 1 step or over 3 steps, when I have a chemical reaction, the total enthalpy change from reactants to products is constant. The other thing is that enthalpy is an extensive property. And if you remember back from first year chemistry, an extensive property is a property that depends on the amount of substance present. So, for example, if you burn a little twig, less energy will be released than if you burn a huge log. That's heat. Enthalpy is an extensive property. Now, we can look at the change that takes place by using enthalpy diagrams, and you should recognize these from kinetics. So in kinetics, we talked about this part. We spent a lot of time on this part of the hill, which, if you remember, the higher the hill, the slower the reaction, because this hill is the activation energy for the reaction. And activation energy is associated with kinetics. Okay, we're not going to worry about the top of the hill. This part we don't care about because enthalpy is a state function, so that means that all we're looking at is the difference between reactants and products. So you notice in this diagram, the reactants have more energy than the products. So energy is released as reactants turn into products. So that difference in energy is the delta H, and since energy is released, delta H is negative. So this is the energy diagram of an exothermic reaction. Likewise, over here, kinetics deals with this part of the curve. We don't care about how high the hill is right now. We'll talk about that and how that ties in at the end of the unit. Right now, all we're looking at is the difference between reactants and products. So you'll notice that the products, in this case, have more energy than the reactants. So the delta H is still defined as the difference in energy between reactants and products. But in this case, delta H is positive because the products have more energy than the reactants. So the other thing we can do, and you should have seen this in first year chemistry, is we can look at the energy change in a chemical reaction. So let's look at this. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. My solid turns into aqueous. And also, over here on the product side, we have 43 kilojoules per mole of energy released, which means that this reaction is exothermic because energy is a product, so energy is being released. Okay, one note, with the new AP exam, this unit is not quite right. This unit would be expressed as kilojoules per mole reaction. It's just a different way to express the same thing. It's a very technical difference. Just remember to write your units that way, and don't worry about why you have to write it that way, because that's more of an academic argument. So if we're looking at this reaction, does the beaker get warmer or colder? Since it's an exothermic reaction and the beaker is part of the surroundings, the beaker will get warmer because the heat is being released by the solid dissolving in water, and that heat is going into the beaker and into the water and into the air. So if the beaker gets warmer, the reaction, as we said, is exothermic. Heat is a product. Heat is being given off. Now the other thing we can do is we can do a little stoichiometry. So if I know I have 14 grams of KOH, I should be able to predict how much heat would be released by those 14 grams. We have enough information here to be able to calculate that. So I know I have 14 grams of KOH, and then the next step would be to change that KOH into a number of moles. So 1 mole of KOH is 56.11 grams of KOH. And then I also know that when 1 mole of KOH dissolves, 43 kilojoules of energy are released. So if I do that math, I get 11 kilojoules of energy to 2 significant figures. So this would be referred to as a thermostoichiometry problem because it's a stoichiometry problem, except instead of having a mole-to-mole ratio, I have a kilojoules to mole ratio.